Let's start the final talk of this morning session. Marc Geiller will tell us about twisting asymptotically flat spacetimes.
Thanks. So thanks Simone, and of course I want to thank the organizers of this great workshop for putting this together and for the kind invitation to speak. And yes, so I will talk about twisting asymptotically flat spacetimes, and this is a joint work with Pouyan Mao and my PhD student in Lyon, Antoine Vincenti. So essentially the talk will be just in two parts, very simple. The first part will be a simple review about asymptotically flat spacetimes, and the second part will be more in depth, talking about what is this notion of twist and why this is useful. So as we know, asymptotically flat spacetimes, they are a very useful idealization, which enables us to describe what we mean by isolated gravitating systems in general relativity. And of course, this is very useful to talk about gravitational radiation, and historically it played a very instrumental and profound role in understanding both conceptually and physically what is the meaning of gravitational radiation. And so now this is the setup which we use for actual measurements, for example, what David talked about. And it's also a setup which has been used on and on for actual proofs of mathematical GR. So theorems in mathematical GR. Now it's interesting because these radiative asymptotically flat spacetimes, they have lots of interesting properties beyond just, let's say, simple gravitational radiation. And these properties, as you know, they are, for example, the memory effect, as we just heard, the existence of an infinite dimensional asymptotic symmetry group. And also, since it's asymptotically flat, it's the perfect context to make link with the X matrix and the soft theorem. And now, as you know, all these things are related through what is known as the infrared triangle. So, okay, very interesting for asymptotically flat spacetimes. And also in recent years, now you see these kind of echoing triangles here, because in recent years, people have realized that there's accumulating evidence that presumably in GR and in other theories, there's an infinite amount possibly of such subleading triangles. So as we heard from David, this is because there are other types of memory effects. From the S matrix point of view, this is due to the fact that the Weinberg expansion in frequency can be, you can probe subleading orders in the soft theorem. And from the point of view of asymptotic symmetries, there is, for example, this work about enhancement of BMS to generalized BMS or possibly to W1 plus infinity. So there is an interesting and rich context which everything happens in asymptotically flat spacetimes. So now, even though this fine list of people here provided very powerful mathematical tools to deal with asymptotically flat spacetimes, and in particular conformal methods which enable to have completely coordinate-free statements, for practical purposes, it's always very convenient to actually choose an explicit gauge and coordinates to do computations. This is what was taught to us by Bondy and his collaborators, and the very powerful idea is to choose Bondy null coordinates like this, and with a particular choice, which is that du is a null vector. So if you impose this, this implies that GUU upstairs is vanishing. And then you further require that XA, the angular coordinates, are constant along the null rays. This tells you that GUA upstairs is vanishing. Then if you combine these two statements and bring them downstairs, you conclude that GRR and GRA are both vanishing. And as a result of this, you can write this very general line element in so-called Bondy form. So this is the same Bondy form as David Nichols wrote, except that I'm using just, sorry for this, slightly different notations, because you will see these are the notations which are closer to the Newman-Penrose formulation. So W is what David called e to the 2 beta, and U is traditionally V over R in the Bondy paper. Now it turns out that this gauge choice, so these three conditions, they're actually enough to solve the Einstein equations, provided you decide on what boundary conditions you want to use. And typically what you also have to choose is the expansion of this transverse metric. So the typical choice for this transverse metric is R2 times the sphere metric. Then there is this important part, which is the shear, and then a subleading expansion. D has to do with logarithmic terms, which were mentioned, and this EAB N are these higher Bondy aspects, which David mentioned. And now what is very beautiful, the kind of the work of these people shown that you can actually solve the Einstein equations, because in this gauge, the Einstein equations, they're organized into a very particular way And in particular, you have three types of equations. So first type of equations are just radial or hypersurface equations. And these equations, they essentially tell you how these functions in the metric have a radial expansion. These are differential equations in R, so when you solve them, you get integration constants, for example, the mass and the angular momentum aspect, and potentially other integration constants which you might want to keep or to throw away. Then you have evolution equations, for example, the famous Bondi-Trautmann mass loss, the evolution of the angular momentum, and the evolution for all these higher Bondi aspects. And then there is a nice argument using the Bianchi identities, which tells you that once you have kind of collected these equations, everything is, in a sense, solved. You don't have any extra equations because through the Bianchi identities, you can show that the remaining equations are actually trivial. So you know that you have exhausted all of the Einstein equations, and you know that you have an on-shell line element. And as we know, near Scri+, if you use this formalism, it's very useful because you can extract lots of precious information. You can talk about asymptotic symmetries, transformation laws, asymptotic charges, algebras, flux balance laws, memory effects, and so on. Now I just quickly mention some generalizations and alternatives to the Bondi gauge, which have appeared in the literature, because what I want to talk about, the twist, is another generalization of the Bondi gauge. So let me first review things which already exist. So the first thing, as you may notice, is that in the previous slide, we only fixed 3 gauge conditions, and you may want to pick a 4th gauge condition. This is typically done by choosing the radial coordinate. And many choices exist, but the 2 popular choices in the literature are the so-called Bondi-Sachs gauge, in which you impose this determinant condition. This actually means that the radial coordinate is an areal distance, or a luminosity distance, as Bondi would say. Then, as an alternative, there is the Newman-Unti gauge, in which you set this metric component to -1. And the meaning of this is that the radial coordinate is the affine parameter for this null vector L. Now, what you may want to do is actually also relax various conditions when you solve the Einstein equations. And this has interesting physical applications. For example, famously, if you allowed QAB to be not a fixed round sphere metric, like in the papers by Bondi and collaborators, this is how you go from the historical BMS group, in which you only have the Lorentz group and super translations. You can extend this to go to GBMS or even BMS Weil, so where you have super rotations, asymmetries, and also Weil transformations. So this you do by relaxing the leading sphere metric QAB. You can also allow this QAB to depend on time. This is useful if you want to describe Robinson-Trautmann solutions like Glenn described yesterday in his talk. It's also useful if you want to describe a radiation in DS or in ADS, because an interesting fact is that in asymptotically flat spacetimes, the effect of the radiation at null infinity is subleading, which is why the shear comes after the leading metric. But if you are in DS or in ADS, the effect of gravitational radiation is actually at leading order. So at leading order in the metric on Scri, in DS or ADS, you have to allow for some fluctuations. Typically, these fluctuating degrees of freedom, you can put them in the time dependency of QAB. You can also put them in this integration constant in the angular direction, which you can keep also for ADS radiation or for some shockwave spacetimes as done by Anna, Katrin Zurek, and Temple. Additionally, what you could do is actually relax the peeling theorem and allow for logarithmic terms in your solution. This is also a possibility. So, okay, in summary, these are some possible enlargements of this asymptotically flat framework, which you can consider with various physical applications. What you can also do is altogether consider a different gauge. You don't have to work in Bondi gauge. For example, you can actually choose to describe spacetimes which are not even asymptotically flat. You can consider, for example, asymptotically cosmological spacetimes, FLRW. This was considered by some people. I think I forgot an earlier reference by Jürgen Ehlers, maybe, who was the first to think about this. Famously, for DS or ADS, you can use the Starobinsky-Pfefferman-Graham gauge. And there's, of course, a huge amount of literature on this. In this list of people here, I just list the people who actually use this in comparison with DS or ADS in Bondi gauge. So this is to compare SFG gauge to Bondi gauge. What is very physically interesting is that you can also use a harmonic or the Donder gauge, because this is typically, as you know, the gauge that we use if you want to characterize the gravitational radiation in the bulk close to the source. Because, of course, in this Bondi formalism, when you look at the Einstein equations, as you know, there is nothing which fixes the time dependency of the shear. This is something which you have to input by hand. So if you want to know what is the behavior of the shear, especially in retarded time, you have to compute this from the properties of the source. And this is typically done in the bulk in harmonic gauge, using this powerful multipolar post-Minkowskian, post-Newtonian formalism. And then you may want to ask the question, as was done by this paper here, the complicated question of transforming these radiative multipolar solutions close to the source towards Bondi gauge at future null infinity. And then once you do this, you can read asymptotically the fine details of the shear and the news, and as typically in terms of the multiples of the source. So this is a very important calculation, which is technically very involved and was only done recently. And of course, as you push further the order in this expansion here in the bulk, the map to Bondi gauge becomes increasingly complicated. And the last technical remark is that even though, for example, if you change the gauge, if you don't work with Bondi gauge, but with Pfefferman-Graham gauge, for example, you could think that this is just a simple diffeomorphism going between the gauges, but actually this diffeomorphism can hide some subtleties and can be a bit complicated to implement. Because typically, if your aim is to actually map some structures in the solution space, or more precisely in the covariant phase space, because in the covariant phase space formalism, you have variational objects like charges and the symplectic structure, you have to take into account the fact that most of these covariant phase space structures, they don't transform tensorially under diffeomorphisms because the diffeomorphism is field dependent. So a very simple example is if you just transform the residual asymptotic killing vector between two gauges, you see that the transformation of this killing vector is not just by the Jacobian, but you have to compensate for the fact that the change of coordinate is field dependent, and you have to act with the asymptotic symmetries on the field dependency in the change of coordinates. So this creates additional complications. So even though you can, of course, implement this and compute these things, this says that maybe it's good to think from the onset about which gauge you actually want to use. Okay, so now we can briefly mention a slight inconvenience of the Bondi gauge to go further. So the inconvenience is that if you study the Kerr metric, so depending on the coordinates that you choose, you will see that it doesn't fit in Bondi gauge. Because for example, in Boyer-Lindquist coordinates, GRR is not vanishing. And in Eddington-Finkelstein coordinates, it's GRA, which is not vanishing, because this contains the angular momentum of Kerr. And because of this, if you want to actually force the Kerr metric to be in Bondi form, this will actually force you to introduce an infinite 1 over R expansion. So this was done in this paper by Fetscher and Loon, and then extended to Kerr, DS, and ADS by Hoek and Virmani. And you will run into the same problem if you actually take the Schwarzschild spacetime and want to perform a super translation of Schwarzschild, it will leave the Bondi gauge. And if you want to force it in Bondi gauge, you will have a metric which is infinite in 1 over R. There's a related subtlety or issue, which is that if now you switch to the Newman-Penrose formalism to characterize these asymptotically flat spacetimes, you have to pick a tetrad, so a null tetrad for the Newman-Penrose formalism. The typical choice is the tetrad which is here. I think in the literature, there's this almost standard term, so it's called the Bondi tetrad. And you see the Bondi tetrad contains these functions which were in the Bondi line element. Here, MA is just some dyad on the asymptotic sphere. And typically, if you use this tetrad now to compute quantities in the Newman-Penrose formalism, you want the spin coefficients, and you also want the Weyl scalars, so the 5 complex Weyl scalars which encode the 10 components of the Weyl tensor. You will find that for Kerr, for example, of course, psi1 is non-vanishing because it contains the angular momentum, which is why, for example, in this W1 plus infinity hierarchy of charge aspects, we call this the spin 1 charge. This contains the angular momentum. And similarly, psi0 is also non-vanishing because for the same reason, if you put Kerr in Bondi form, Kerr has a non-vanishing shear and subleading terms in the angular metric. Of course, this shear does not depend on you because Kerr has no radiation, but this shear is just an artifact of the fact that you're trying to force Kerr in Bondi gauge, and therefore in the transverse metric, you have an infinite expansion which depends on sine theta, cos theta, and so on and so forth.
Can you not get rid of this shear by just doing a super translation?
That's a good question. I don't know the answer.
You should be able to get rid of this shear by doing a super translation.
Maybe just the shear, but not the subleading terms, I guess.
No, not the subleading terms, I don't know, but
maybe the shear.
I mean, the solution is stationary, so it admits good cut, right?
Probably the shear you can, yes. But not the subleading terms, yes. So now why I call this a puzzle? This is a slight puzzle because... Yeah, you can.
So you mentioned this issue with 1/r expansions for doing these in the Bondi gauge, but
Yes.
I thought the purpose of Bondi gauge was to do 1/r expansions. So why is it a problem that these have an infinite 1/r expansions? Or is there a problem like connecting this into like continuing into the bulk singularities? Or?
Yeah, so maybe I shouldn't have called it a problem because it's not a problem. It's just we can say a technical inconvenience, because of course Bondi is 1/r, but it's 1/r because you want Bondi to describe very complicated things, and Kerr is not should not be a very complicated thing, because Kerr there's a metric in explicit closed form in 1/r, so it's unnatural to make this metric infinite in 1/r. So just in this sense.
Right, thank you.
Okay. So now why this observation is kind of a puzzle? It's kind of a puzzle because so the reason why this happens and why this is a puzzle is that if you look at the principal null directions of the Kerr spacetime, well, these principal null directions have what is geometrically called the twist, and these principal null directions, they don't actually generate null hypersurfaces. And more precisely, there is a deeper reason. Kerr is an algebraically special solution of Petrov type D. So if you actually choose the tetrad which is aligned to the principal null directions, you actually have that psi0 and psi1 are actually vanishing for Kerr. So the fact that psi1 is vanishing is at odds with the fact that here psi1 contains the angular momentum. And the reason is that the psi1 here is not built with the same tetrad as the psi1 which is here. So there is this mismatch of tetrads which we usually use for let's say Newman-Penrose in Bondi gauge and the Petrov classification, for example. And so it is this slight mismatch of choice of tetrad, which is this inconvenience. And this is the inconvenience which you can precisely fix by introducing a twist in the spacetime. So geometrically, what the twist means is that you allow for this Newman-Penrose coefficient rho to have an imaginary part. So doing this means actually merging what we mentioned on the previous slides, the work of Bondi and collaborators, all these references with some of the things you find in papers by Petrov and the book by Chandrasekhar, and also this book on exact solutions by these people. This is just a reminder of the picture from Chandrasekhar. You have Im-Rho here, which is the rotation here, so the twist. Sigma is the shear as usual. And in terms of the null vectors, this is the definition of rho and of sigma. So you see that they're both measuring something about this null tetrad, this null vector partial r, but you are, for the shear, you're projecting on M and M, and for rho, you're projecting on M and M bar. So both these things are complex. Sigma encodes the 2 degrees of freedom of gravitational radiation asymptotically. And rho has a real part which encodes the expansion and an imaginary part which is precisely the twist. Okay, so now I will jump to twisting asymptotically flat spacetime. So if you have questions, maybe that's a good moment to stop for questions. Yeah.
Super translated Schwarzschild in Bondi gauge has extra terms in the VV and the angular components and so on turned on, but not RR? Or is that
No, not R. It's RA actually. But I will go back to this at the end. I will mention this at the end. Yes.
Sorry, is this F the one from the Goldberg-Sachs theorem?
The which one?
The L you're taking us to define the shear?
Yeah, you mentioned this Goldberg-Sachs theorem. So indeed, for algebraically special solutions, if you impose psi1 and psi0 to be vanishing, Goldberg-Sachs tell you that there is a shear-free congruence of null geodesics. So sigma is equal to 0. But yeah, this is L. Yes. But before going there,
so isn't rho 0 for this L?
No, it's not 0.
I thought it was shear-free. I see.
But not. Yeah, shear-free, but exactly, but not expansion or twist-free. I will show some more explicit expressions, maybe.
Sorry, I didn't understand. What's the relation between the twist and the shear? They're not.
Yeah, they're not the same thing. They're just different. They're not the same thing. Yeah, the rho has M bar here, and the shear has M and M. That's the. Okay, so this was a small motivation to introduce the twist. Now we can introduce the twist. Exactly. Yeah. Yeah, so initially you can just think of the twist as being precisely sourced by this component GRA, which is non-vanishing. So you call this LA. This is kind of standard notation in the Stefani book, for example. You call this LA. You put this in the Bondi metric to be non-vanishing. Actually, such terms in the Bondi metric have actually already appeared in the literature. For example, in 3 dimensions, there is this derivative expansion gauge by also some people in the audience, Marius and Romain. In 4 dimensions, Marius, Romain, Andrea, Simon, Mathieu had this gauge called the covariant Newman-Unti gauge, which is exactly a gauge in which you introduce this GRA component. There is also very recently this paper by Geiller, Herben, about the 4D Carroll covariant Bondi-Sachs gauge. And I think Geiller will talk about this tomorrow, presumably. And so because Geiller will talk about this tomorrow, I didn't give so many details. Maybe Marius will also mention this. I'm not sure. But Simon, okay, maybe, yeah. So, but you see these gauges in 4D are called covariant because part of the motivation of this work was to restore some Carolian structure on Scri+ to kind of see geometrically more naturally some of the Carolian covariants on Scri+. Here the goal is to bring things a bit closer to the Bondi spirit and to the Bondi language. And the goal was to have kind of the full dictionary between everything which you can compute. So the Newman-Penrose formalism, the metric formalism, compute the symmetries, the charges, the evolution equations, all these things. So fill in some of the details. So now you need a strategy for this, because if you actually blindly just turn on GRA in the Bondi metric, if you look at the Einstein equations in Mathematica, they're all completely entangled, and it's not clear to see how you can solve them because all the components are now mixed together. So you lose this, this Bondi hierarchy of hypersurface equations, which I mentioned in the beginning. This is not nice. So the way to actually fix this is to go back to the tetrad, because in the tetrad, so in the Newman-Penrose formalism, introducing the twist just means introducing this du component in the complex tetrad M. So you just turn on this du in M, and this essentially introduces a twist for you. But the subtlety is that if your initial tetrad is this, if you compute the metric now, if you put this L in the tetrad, you see that in the metric, L appears, well, essentially almost everywhere. And it's because L appears almost everywhere in the metric, if you put L in the tetrad like this, that if you actually use this metric to solve the Einstein equations, then you recover this Bondi structure of the Einstein equations, and you can actually solve them. So you should not just blindly turn this on. I'm saying that the metric is equivalent to this because you see that this omega here has disappeared from the metric. This is just a very technical remark, maybe for Glenn and Romain, because usually in this Newman-Penrose tetrad, there is this omega coefficient here. The only purpose of this omega here is to actually solve the Newman-Penrose equations by setting the spin coefficient pi to be vanishing, because then the equations simplify. And if you want to set pi to be vanishing, you have to put omega here. But if you put omega here, you have omega in the metric everywhere. And if you have omega in the metric everywhere, it's not clear how you fix omega, because there are only 4 hypersurface equations. And these hypersurface equations, they can only fix u, x, and w. So there's no equation which can fix omega. And the reason is that omega can actually trivially be reabsorbed in a redefinition of the variables, which is why here I wrote equivalent to, and omega has disappeared. Because from the metric viewpoint, you don't actually need omega. And the last notation is that this dyad on the sphere M produces this metric gamma AB. So this is the metric which has the Bondi expansion which we saw in the beginning. And you see that if you have twists, GAB is not equal to gamma AB. So this introduces some extra complications. You see the twist appearing here everywhere. So now you can actually go ahead and solve the Einstein equations. You can do this in the Newman-Penrose formalism.
Maybe about, just to clarify your strategy, if you're not fixing the gauge in the bulk, solving the Einstein's equations will have arbitrary functions of time. So what do you, how are you going to deal with them, and how are you going to interpret the solutions? You will need to fix the gauge at some point.
I'm still fixing some things, you will see. Yeah, I'm still fixing, yes, some conditions. On the next slide, I will fix some conditions. Now, I just want to mention that the reason why I want to go back and forth between Newman-Penrose and metric is that the Newman-Penrose formalism is extremely efficient. You just turn the crank and solve all the equations. but it obscures many things, in particular, the nature of the gauge conditions which you are imposing, the nature of these no-log conditions. If you want the spacetime to be not polyhomogeneous and not have logarithmic terms, you have to fix some precise terms in the expansion of this metric. In Newman-Penrose, it's not really clear what this expansion is. It's clearer in the metric language. And also to have this Bondi hierarchy of equations, to be 100% sure at the end of the day that you didn't forget any equations, it's useful to do this, I think, in the metric language. And also the goal is to just extend the familiar Bondi expressions to the case of non-vanishing twist, because I think unless you read directly the Newman-Penrose equations, sometimes they're a bit hard to translate in metric language. It's nice to also have the standard metric equations with non-vanishing twists. And you will see why in a minute, because now we can build the solution space in Newman-Penrose form. And now what is usually very convenient and customary in Newman-Penrose is to actually solve the equations by choosing these gauge fixing conditions. You can always do this because kappa equals 0 means that means essentially that dr is a congruence of null geodesics, which is the case here. And then when kappa is vanishing, you can always perform Lorentz transformations to set pi and epsilon to be vanishing as well. So without loss of generality, you can choose this. The geometrical meaning of this is actually that the whole tetrad is parallelly transported along L when you go in the radial direction. That's the geometrical meaning. Now the point, I will flash this briefly because I don't want to use this. The point is that if now you turn the crank and solve the Newman-Penrose equations, you get a lot of structure. You get a lot of structure because Newman-Penrose equations, they are first order equations as opposed to second order in metric form. And there are equations on scalar quantities instead of tensorial quantities. So because of this, you have many more objects and you have to define all these things and get equations for them. And when you do this, you get, first of all, the expansion of the Weil scalars, then you get the spin coefficients, then this involves some definitions which are here, then you have to reconstruct the tetrad, and then you have to get the evolution equations. So there's lots of things which you have to combine together. So I won't go through the details, I just want to summarize just the key features of this solution space in a Newman-Penrose form, just to see what it actually contains without giving explicit expressions. So the first feature is that if you introduce this twist, the peeling is preserved. This was on the first thing which I showed, the expansion of the Weil scalars. The Weil scalars, they have the usual peeling behavior. So you don't violate peeling by introducing the twist. Now the twist itself, how does it actually appear? It appears, as I said earlier, in imaginary part of rho. This quantity is usually called sigma. And what is sigma? Sigma is actually defined like this. So this is in Newman-Penrose form. And if you translate this back to kind of metric vectorial language, you get this quantity here. And tilde is just the dual of L with respect to the leading metric. And now what is this, this operator here? This operator here, this big D is just a generalization of the standard Newman-Penrose et operator to the case of non-vanishing twists. So this big D is just a standard et plus these two terms. Now what is this gamma 0? This gamma 0 is the fact that I have allowed QAB to depend on time. This is to include Robinson-Trautmann solutions. So if you do this, you have gamma 0. And the last point, but this is just a technical side remark because I thought it was cute. You can actually show that if you have twist, but if gamma is vanishing, so if QAB does not depend on time, you can actually also build the analog of this Newman-Penrose 10 exactly conserved quantities. So Newman and Penrose had this paper about 10 exactly conserved quantities, which have to do with the subleading term in the expansion of psi 0, so the psi 0, 1. And you can show that if you have non-vanishing twists, there is a generalization of this formula, and these charges can still be defined. So I thought this was interesting, that introducing the twist does not violate this property. So now I just want to mention some of the properties of the solution space in metric form. And as I said earlier, even though, of course, we know that the metric is just the square of the tetrad, you could think that, of course, if you know the, yeah.
They are still the same 10 exactly conserved, right? Or it's just,
I mean that there's a new expression, but the expression satisfies the same property, namely that it's identically conserved non-linearly.
okay.
It's
There are still 10.
Yes, yeah, it's still, yes, still 10. But then linearly, you have infinitely many, just like in the standard case without twist.
But since you're just changing the gauge you're using, why do you find that surprising?
Well, because to actually compute them, it's you have to combine It's a bit
No,
non-trivial.
I understand that in random gauges, you can make the equations look very complicated, but the physical properties should be independent of the gauge. So, now, because I think you answered to the previous question by saying that you don't have arbitrary functions of time, so you are fixing the gauge in some other way, which is not just the usual Bondi coordinates, right?
I will write actually now in metric form what I'm fixing.
Right.
Yes. Yes.
Okay, thank
So
you.
you will see, yeah. Yeah, so even though the metric and the tetrad are just related by this, you could think that everything in Newman-Penrose is easily obtainable in metric form, but this is not really so because the transformation can be a bit painful, and it's instructive to transform things back into a metric language. For example, if you do this, you can see that the gauge fixing is actually complete. And what are the gauge conditions in metric language? Well, as you saw from the metric, even if you have twist, you still have GRR, which is vanishing. Since in Newman-Penrose we imposed epsilon to be vanishing, in particular you have the real part of epsilon which is vanishing. This actually implies the Newman-Unti gauge condition. Real part of epsilon vanishing implies that GUR is equal to -1. In Newman-Penrose we impose this, kappa equals 0, but kappa bar equals 0 actually implies that this twist LA, this twist vector, does not depend on R. So this is how the radial dependency of GRA is actually fixed by this condition. And actually, you can nicely combine these two conditions here by this simple condition on the Levi-Civita gamma, which is that gamma mu RR is actually vanishing.
L was a parameter in it entered in the linearly in the metric.
In GRA, yes.
So your gauge fixing is as zero modes. It's not complete, right?
It has zero, exactly, yes.
Okay.
Yes, and you will see this in the symmetries, yes. Exactly. And then if you do this, you can, of course, now explicitly recompute the transverse metric gamma and see what it means to have no log conditions. As you may know, also in this metric gamma, if you impose the Bondi-Sachs or the Newman-Unti gauge condition, as also David mentioned, the tensors which appear in gamma have some of their traces which are fixed, and the fixing of these traces actually depends on the gauge. It's useful here to go from Newman-Penrose to metric to actually see what is this fixing of the traces. Otherwise, in Newman-Penrose language, it's a bit obscure. You don't have direct access to gamma AB in a sense. And then, as I mentioned, you have a complete control over the Bondi hierarchy of Einstein equations. You know exactly what is a radial equation, where are the evolution equations, and then using the Bianchi identities, you can show that all the other equations are trivial. So at the end of the day, you know that you have exhausted all of the Einstein equations, and there is nothing left. And now what is nice is that you can write the flux balance laws in, let's say, a familiar form. Unfortunately, this we could not achieve in the very general case, but there is already an example which is a bit non-trivial. If you remove the time dependency in QAB, you set gamma 0 to 0, you take the twist to be time independent, you can recover this kind of standard Bondi expression where the energy here is the Bondi mass plus some actually fairly complicated terms. You can massage the flux balance law in this form where the right-hand side is up to this is negative definite. So which is nice for the flux balance law of the mass. Yes?
So what's the transformation law of your E equals M plus complicated stuff? Does it transform nicely under your asymptotic symmetries?
I don't know, on top of my head, I don't know. I can reconstruct it for you, but like
okay.
that,
Okay, sorry.
Yeah.
That's it.
And sorry, did you say what the script J is here? Is that something that's
so
linear induced?
yes, I didn't say what script J was. Script J is essentially the vector version of psi 30. So it's the quantity which, when contracted with the frame M bar, gives you psi 30.
You said you're allowing gamma to be time dependent?
But not for this formula. In the general case, yes.
Right, okay.
Yes. Yes. Yes, relation between L and LA is just because I'm going back and forth between Newman-Penrose and metric.
So you
in
contract
Newman-Penrose, L is a complex scalar, and in metric form, this is just a vector. So
okay, you
it's the same
contract
amount
with
of
the
information.
diagonal.
Yeah, if you contract LA with the frame on the sphere MA, you get the complex L. So I'm just going back and forth. Yes? It is. It is GRA. Yes.
No, because otherwise
it is GRA because it's this.
In the metric, it appears in a very specific combination.
Yeah, but it's GRA because in Newman-Unti gauge, GUR is -1. So GRA
right,
is
right,
identically
okay,
L.
I see.
Yes. Okay, so yes.
Is your related to Adrian? Is your E related to psi2, the leading term psi2, or
Yes, this M is real part of Psi2.
M is the real
This M,
part?
and this complicated thing is
So it doesn't transform probably
yeah,
in a
exactly.
very nice way.
Yes, which is why to write this in Newman-Penrose form, it's less obvious. It was easier to write it in metric form. That's just why. Okay, so now that you have a complete characterization of the solution space, I won't write the solution any further, but from all these ingredients, you can, and in the paper, you can write the metric. And the very convenient thing about having the dictionary between Newman-Penrose and metric is that you can now, this is also true without twist in the standard Bondi thing, is that if you want the metric to stupidly subleading order, it's extremely convenient to do this in Newman-Penrose, because in Newman-Penrose, you just do a Sudoku, you just combine equations and it's completely algorithmic. And then with this kind of map using the tetrad, you just convert everything to metric form, and then you get the metric to whatever order you want. So that's why it's nice to have this explicit dictionary between everything. So now the next natural thing to do is to look at the asymptotic symmetries of these spacetimes with twist. And to do this, you just follow the very familiar construction, namely you look at vectors such that when you act with these vectors with the lead derivative on the metric, you preserve the gauge and the fall-off conditions. If you do this, you find something very familiar. You find that in the U component of the vector field, you have this thing called F, which is a pure supertranslation plus U times Weil transformation. There is this small field-dependent shift here. This is just for a technical reason. You can actually put this such that the vector fields, they close on an algebra and not on an algebroid. So this you get by putting this shift. And then you get, the familiar thing that the radial part has the Weil factor and then an expansion, and the angular part has the super rotations. But at subleading order, this epsilon A is now free. So this epsilon A, which is free, is here because in the solution space, the twist is free. So because you have a free function in the metric, you have a free function in the residual vector field. That's just how it works with these asymptotic symmetries. The very important thing is that the subleading terms here, they all depend on this 1/r term epsilon. And this will be extremely important in 1 second. So this is why I wrote it in this form. Now you can compute the transformation laws of various objects in the solution space. And in particular, you can compute how this twist LA transforms. And the twist transforms, well, in this familiar way with the lead derivative. Then there is a Weil weight. And then there is an anomaly. And the anomaly involves epsilon itself and the gradient of F. Now, this is a very kind of consistent formula because you see that, well, the first thing you see is that you can actually now use this symmetry epsilon to actually set L to be vanishing, which seems that you go back to square one because you actually turn it back off, because of course, asymptotically, you can always use this residual symmetry to turn off the twist. You can do this, and this is the meaning of this formula. What you also see is that if you set the twist to be vanishing, you set L to 0, L to 0, by consistency, epsilon must be del F, and if epsilon is del F, in here you recover the standard formula for the asymptotic vector field in Bondi gauge. Yes?
You mentioned you compute the charge. Is it a large gauge transformation or a small gauge transformation for the epsilon?
It's large.
It's a large one.
So there's a non-vanishing charge associated to this. Yes. I won't talk about the charges except at the very end. So now why this is important, the transformation laws, because there are two very useful transformations laws to look at, which is how psi 0, 0 transforms and psi 1, 0. So the leading of the Weil psi 0 and the leading of the Weil psi 1. They transform like this. There's always an homogeneous part and then inhomogeneous terms. So they transform like this. So now why I mentioned these transformation laws and why I put this asterisk here is that now what is now very natural in this extended solution space with twist is that now you can look at algebraically special solutions. Because algebraically special solutions, by definition, there are exact solutions of the Einstein equations, which have psi 0 and psi 1 identically vanishing. And then, indeed, by the Goldberg-Sachs theorem, this implies that the Newman-Penrose sigma is actually also vanishing. But now you see that because of this transformation law here, so this term is homogeneous. So this one, if you set size, so in the algebraically special case, this is identically 0. There's no problem. But in the algebraically special case, psi2 0 is not 0. This is, for example, the mass for Kerr. So if you set psi1 to 0 to be algebraically special, you have to set upsilon to be vanishing. And if you set upsilon to be vanishing, because of the form of the vector field here, everything disappears and the vector field truncates and has a finite form. So this is how you get immediately that if you reduce this solution space to the algebraically special solutions, this asymptotic killing vector truncates and has this exact form here. And you have, again, pure super translations, Weyl transformations, and super rotations. Now, what is very nice is that the solution space also truncates if you go to algebraically special solutions, a bit to mirror what happens to the symmetries. The solution space truncates. And it truncates because it's easy to see in Newman-Penrose form, but you can, again, transform everything to metric. It truncates because everything becomes an expansion now, not in 1 over r, but in 1 over, so a finite expansion in 1 over r plus I epsilon. So I epsilon is real because epsilon is purely, r plus I sigma. So the twist sigma is purely imaginary, actually, so this is real. And the expansion involves manifestly sigma. And just to give you an idea of what it looks like, if you compute rho, for example, rho has a finite expansion, and rho is just 1 over r plus I sigma. Psi0, psi1 are vanishing because it's algebraically special. Psi2 has this form, psi3 has 3 terms, and psi4 has 5 terms. And everything is truncated. And what is nice is that now you can infer everything you want about these algebraically special solutions, absolutely everything from just the algebraically general case, because you just, in the algebraically general solution space, you impose these speciality conditions, and you get back to this. At the end of the day, this algebraically special solution space is controlled by what? Well, by just 2 things, the time-dependent twists and the dyad on the leading dyad on the sphere. So this is the celestial metric M, which can also depend on time. And there is only a parameter, which is the real part of psi2 0, so the mass, and this mass has to satisfy constraints in an evolution equation. So these are the typical constraints that are obeyed by real part of psi2 0 for algebraically special solutions. So these constraints are complicated to solve, but by solving these constraints, this is how you can actually generate exact solutions of the Einstein equations, which are algebraically special. And just as a remark, because the case is very general, you also have this dual mass imp psi2 0, which is also non-vanishing. And if you look at the transformation laws of, so there's another spin coefficient which I didn't mention, it's tau. If you look at the transformations of L and tau, you can actually see that even if sigma and the news lambda are vanishing in these algebraically special solutions, sigma and the news lambda are actually replaced by the twist L and the spin coefficient tau. This is what plays the role of shear and news for the algebraically special solutions. And now, as a very simple minded application of this, as an example, one can consider super translated Schwarzschild spacetime. So we can get super translated Schwarzschild by just by starting with the Schwarzschild metric in null coordinates and doing a finite redefinition of the retarded time u. And this redefinition depends arbitrarily on the angles. So this is, if you do this, you get back to the Schwarzschild metric and you get back to these terms, which I isolated to be proportional to this contribution. And in particular, you see that here there is a GRA component, which is why the super translated Schwarzschild solution is not in Bondi gauge. Yes.
I may comment or ask. That is only because you chose an extension of your symmetry vector field at Scri, which does not preserve Bondi coordinates. If you do, you have subleading terms in 1 over r in the extension of your diffeomorphisms, and then you should get it in a way that does preserve the Bondi coordinates. Take the form, you know the expression that you find, for instance, in his paper with all the subleading terms of psi? Those are chosen so that you preserve the Bondi coordinates in the bulk. So if you use that instead of this trivial extension, which is 0 in the bulk and does not preserve Bondi coordinates, I bet you will.
I would like to see it, but I doubt.
The super translation on Schwarzschild has also been done in these papers by Andy, Hogging, and Perry, and there was no RA or RR component turned on, and everything was in Bondi gauge.
Probably the DD has a.
Yeah.
Okay, okay. But so
We
there's
you
a,
can.
okay, so maybe there's a resummation, like because the you have the radial
Just
dependency of the vector
updating
field.
terms.
Yeah.
I mean, I think I agree with everyone, but just to say that here you do that, but like you can show that you can put super translated charge shell in boundary by an extra gauge transformation. That's the exactly because adding a twist is by a gauge transformation. So the thing is that maybe it's more convenient to write it with a twist for things.
Yeah,
Mark
it's,
is
sorry,
doing.
I should have made this point. This is just a point about convenience, right? It's not, I mean, it's not, this is not a point about, no. And I also mentioned here yeah, so my bad, I should have put more references here probably, but I just mentioned compare long, and they wrote expressions like this in different coordinates, and of course you can do this, yes. Yes.
No, so yes, Mark, sorry, so if I may comment, the thing which is nice about your expansion here is that you have this capital epsilon A symmetry, but you can gauge fix by equating it to the gradient of F. And then you are back in boundary gauge.
Yes, exactly, yes.
Is that what you are doing? So you are.
If you did this,
Yes,
you'd be back in boundary gauge, yes. Yes.
Exactly, okay, yeah.
Thanks. Yeah, just a comment on all these discussions. So from a Carroll perspective, these transformations, they're really very natural because you can show, well, on an earlier slide, you had this epsilon, which that's actually a Carroll boost.
Yeah.
And when you ask for an asymptotic killing factor, that Carroll boost depends on the supertranslation parameter. So this partial AC, that's just a Carroll boost. So from a boundary perspective, what all you're doing is just allowing for all Carroll frames,
yes,
essentially.
Yeah. Yeah, thanks. Yeah, thanks for the comment. Yeah, so again, this is just a simple, straightforward, application, because then, yes, what you just get now completely trivially from this without having to really do anything is just two-line computation. You get immediately that you compute some charges, you choose the ER wall prescription, and you find that the charges don't depend on the radius, and have this expression, and you recover this fact also pointed out here, I think, that because you have performed this super translation, the charge pick up a super rotation component now. So you have this, you get this YA, the del C component in the charges. And now what is convenient is that you can actually also do this for super translated Kerr-Taub nut, for example. For Kerr-Taub nut, the twist sigma would just be this A cos theta minus the nut parameter M. And so this is maybe where actually it's maybe more useful to do it in this language than insisting on sticking to boundary gauge, maybe for Kerr. But I don't want to give details about Kerr. And okay, so I will just conclude here. So I wanted to argue that we can build a complete Newman-Penrose and metric characterization of this algebraically general solution space with non-vanishing twists. Then there is a very natural truncation of this and reduction to algebraically special solutions. You can also, of course, do this in 3 dimensions with non-vanishing cosmological constant, and it's fairly straightforward. Everything goes through as well. And I think this kind of brings now interesting perspectives. So I spent some time describing this. So as the things you could do for the perspectives, of course, you can study various extensions, which I mentioned in the very beginning. In 4 dimensions, you can choose lambda to be non-vanishing. You could put logarithmic terms coupled to matter, consider asymptotically cosmological spacetimes. You could also try to ask how this relates to a near horizon construction, especially for algebraically special solutions. The study of the charges, we need to make it a bit more precise. What could be interesting would be to reproduce this computation of Blanchet, Compère, Fay, Oliveri, Serrage to bring radiative solutions from harmonic gauge to the boundary gauge with twist, because so this I'm not sure, it's just speculation, but it could be a bit more natural to actually take these solutions in harmonic gauge to boundary gauge with twist. I don't know if when you do the diffeomorphism to boundary, you naturally end up with a twist or not. What I know is that naturally you end up on the Newman-Unti gauge, for example. So if you insist on having the Bondi-Sachs gauge and not the Newman-Unti gauge, you have to perform an extra diffeomorphism. So it could be that naturally you end up with a non-vanishing twist. This I don't know. Maybe this could be useful for numerical relativity and for the maybe Cauchy characteristic extraction, because this relates heavily on the choice of tetrads. So maybe a twist could be useful. could also be useful to have more geometrical and coordinate-free statements following the spirit of Garrosh, and to see if all the things we have heard about subleading symmetries and W1 plus infinity can also exist here. And the last thing I want to mention is that I think this is maybe an interesting place to study, at least for algebraically special solutions, the interplay between, so the potential interplay between asymptotic symmetries and these so-called hidden symmetries arising from symmetric killing Steckel or anti-symmetric killing Yano tensors. Because, for example, we know that for algebraically special type D spacetimes, there is this general expression for the this quantity K is actually a killing Steckel tensor, so it's a symmetric object which satisfies the symmetric killing equation, tensorial killing equation. And from this quantity, you get a conserved quantity, which is the famous Carter constant. And this exists for any type D spacetime. What is nice here is that this construction uses the metric and also these principal null directions. So you can only do this explicitly if your tetrad corresponds to the principal null directions. So if you were doing this in Bondi gauge, you would run into the same problem that Bondi Kerr is not exact, so the G mu nu would be non-exact here. So all the statements made about this killing tensor would be in 1/R. Whereas here you can make all these statements exactly in R because you're using a tetrad aligned with the principal null directions. And thank you. Questions?
So yes, Mark, thank you for the talk. I have a question about what is charge and uncharge in your asymptotic deformorphism, because your choice of gauge, allows nicely to separate, to follow on Yele's comment, the Carroll boost, which are this upsilon, and the supertranslation, which are generated by this F. So could you tell us about what into these two symmetries is charged and what is not actually? Or if they are both charged?
They're both charged.
Okay.
Except that the charge is it's immensely lengthy to write down. So I can tell you some properties of the charge in cases where the metric does not depend on time, or if the metric is round. In the completely general case, the mathematical output is 10 megabytes. So.
Okay, because from a Carroll perspective, now we understand that in fact the BMS supertranslation is coming from an interplay between the upsilon and the F actually. So I was wondering if this supertranslation charge, which is a fundamental object that is really interesting, was coming from one or another symmetry. But you said that it's impossible to disentangle even in your choice of gauge. That's
yeah, I would have to think about it a bit more. But
okay, yeah, thank you.
Maybe a short follow-up, but would you agree that if you have a characterization of the asymptotic symmetries in terms of preserving some universal structure in a gauge-independent way, then your charges should be the same as the usual ones with no extra ones? Or are you changing the universal structure in some way in doing this?
Yeah, I'm actually not sure. Yeah, so I don't want to give a wrong answer. I would tend to agree that it shouldn't change, but I cannot see how it would work such that it doesn't change. So,
could you elaborate maybe on the subleading symmetries and W1 plus infinity? What you have in mind in this formalism?
Yeah, what I had in mind was the fact that if you kind of want to extend to the realm of symmetries, what happened with these W1 plus infinity symmetries. So for the charge aspects, we went from spin 0 to spin 1, then to spin 2, and so on. Then the parameter corresponding to the spin 0 is a scalar. The parameter corresponding to spin 1 is a vector. So you could think that the parameter corresponding to the spin 2 symmetry is a tensor. So the natural thing to look at would be killing symmetric or anti-symmetric type of tensors. This could also explain why these spin 2 symmetries and subleading are not manifest in as space-time symmetries, because if they come from higher ranks, like tensorial symmetries, killing tensors, these would be hidden symmetries in some sense. So this is why there could be a relationship, but yeah, I could not make it work any better. But maybe this is a setup to make it work, because now you can make some more exact statements about some solutions at least.
So here you've been playing about generalizing, relaxing the gauge. This one seems very natural. Do you have any idea about, should we still generalize one more? Do you have any intuition about something that still should be done, or?
Yeah, you can surely generalize again because, so for example, one thing you can straightforwardly do is that I said that fixing kappa to 0 means that the twist L does not depend on R, but actually you can solve the Einstein equations even without imposing this condition. So the twist can have an arbitrary R dependency, and you also don't have to fix radial coordinates. You don't have to choose Newman-Unti or Bondi. So you can actually have a much more general solution, but I think the only way to settle this question is to ask computation like this one, to actually see for, physically realistic solutions that we understand, at Scri plus, what does this buy you? Does this extension allow to repackage some terms which would be otherwise complicated in standard Bondi gauge? That's the...
Yeah, it's just a quick comment on the killing tensors. So in the realm of the self-dual gravity solutions, like self-dual tau nut, where we actually expect these W symmetries to apply, the killing tensors become reducible. So they become the square of killing vector. So it's not really giving like an extended object. So there is a Laplace Runge-Lenz vector, and that's essentially what these are.
Okay.
Any more questions?
Yeah, any question?
Question from the organizer, nonetheless.
So, but for these algebraically special solutions, are there also killing tensor of higher rank or not?
For other type than D?
Yeah. No, for this type. So here you have a rank 2, so you, higher rank.
On top of my head, I don't know. There's probably some, there's a lot of forgotten cryptic literature on this. So I'm sure someone has cooked up something like this, but maybe it's not so.
Because to go back to the relation with W1 plus infinity, you would expect more killing symmetries. No?
Yeah. I would already be happy with some spin 2 type of thing, but maybe there's higher, yes.
I think 4 dimensions, the ranks in higher dimensions, the ranks go on up. But in 4 dimensions, I think it's just rank 2, but you have a killing Arno tensor as well in the special cases. So the Kerr family is distinguished also by having the extra conserved quantity. So the general type D is conformal killing tensor. Kerr and friends it's got an honest killing tensor.
I mean, there's also this property that you can build a trivial killing symmetric killing Steckel tensor by just taking the tensor product of killing vectors. This would be trivial for exact killing vectors, but it could be that for asymptotic killing vectors, it's not trivial because asymptotic killing vectors do something on the solutions. So maybe if you build higher rank tensors by taking asymptotic killing vectors, you get something non-trivial, but this I don't know either.
I'm curious about why you think this could be useful for numerical relativity, because naively, one could think that in this gauge, it's going to be harder to know where caustics form in the bulk, and so where the coordinate chart breaks down.
Yeah,
so at first sight, it looks like less good, but maybe you have some...
to be honest, I added this point during David's talk, so... No, but because I've seen many papers by the team in Caltech, for example, the team of Tucholsky, where they actually discuss a lot the properties of the tetrad that they use, and the fact that sometimes with technically, I'm not actually sure what is going on, but that they want to actually measure errors in numerical codes arising from the fact that you use more or less convenient choices of tetrads. So,
So let's thank Marc again for twisting the whole audience.